In this lecture, we will apply some of our previous findings on an example. Okay? Especially, we will remember the relation between the eigenvalue locations of the A matrix and the behavior of the state transition matrix corresponding to that A matrix. Okay, so suppose we're given the following system through a block diagram representation. Okay, consider the below block diagram, where we have an input first entering a sub-block, and then that produces a signal, and that signal is fed to an integrator and a little bit more sophisticated subsystem whose transfer function is this. Okay. And then those two separate signals are combined to produce the output of the system. This is the input U, and this subsystem has the following transfer function. Okay, so for this system, okay, with input and output scalar and defined through this interconnection of subsystems, we have to first obtain a state space representation okay, for this system. Namely, we will obtain four matrices A, B, C, and D of appropriate sizes, for which the transfer function from input U to output Y matches the transfer function, the overall transfer function that's described by this block diagram. Okay, so once we have that representation, in part B we're asked to look at the system matrix, the matrix A, for the matrix A that you obtain in part A. Determine the Jordan form or the Jordan matrix indicated by J. And by looking at that Jordan matrix, we are also asked to discuss about the behavior of the state transition matrix corresponding to this system. What can be said about the behavior of e to the AT as t goes to infinity? Okay. As t goes to infinity. Okay. Now let's begin with part A. Solution A. First, what we will do, we will obtain the transfer function, the overall transfer function, from that input to Y. Okay, by simplifying that block diagram into a single block. And once we have the transfer function, we will figure out a state space representation for that, and we will choose, okay, well, I will choose the controllable canonical form. Of course, there are many other ways to obtain a state space representation. Note that we're using the word A here, not instead of V, because for a given transfer function, there are infinitely many state space representations. Okay, from the transfer function to state space, there are many ways to go. However, for a given state space representation, there's always a unique transfer function. Okay, so first we will therefore obtain the transfer function, and then by applying the method of obtaining controllable canonical form, we will obtain an ABCD matrix, okay? And then we can move on to part B. Okay, let's obtain a transfer function. G of S equals the ratio of the Laplace transforms of the output and the input. Okay, so Y of S, this signal, okay, well, the Laplace transform of that signal equals Laplace transform of this signal plus Laplace transform of that signal, okay? And this signal is this signal times, well, okay, we're in Laplace domain, this signal times 1 over S, and likewise, this signal is this signal times this transfer function or sub-transfer function, and the signal here is simply input multiplied by this transfer function, 1 over S squared plus omega squared. Therefore, Y of S equals 1 over S, okay, times the signal here, which is 1 over S squared plus omega squared U of S, okay. So it's this signal, and plus this signal here, which is 1 S over S squared plus omega squared times the same thing, 1 over S squared plus omega squared times the input. Okay, so if you write this as Y of S equals something times U of S, and that something must be the transfer function. So let's do that. So this equals 1 over S plus S over S squared plus omega squared times 1 over S squared plus omega squared U of S, okay, and that equals, let's write this as a single fraction, which yields 2S squared plus omega squared over S squared plus omega squared times 1 over S squared plus omega squared times U of S, okay? For this thing here is our transfer function. So let's write it here. G of S, okay, equals this, okay, because that equals Ys over U of S. So G of S equals 2S squared plus omega squared over S squared plus omega squared square, okay? And if you write the denominator polynomial in its open form, we have S to the 5 plus 2 omega squared S cubed plus omega to the 4 S. Okay, so that's the transfer function. And once we have the transfer function, now we can apply our favorite method that takes us from the transfer function to the state space presentation. And for this example, and for no particular reason, we're going to apply the controllable canonical form representation algorithm, okay, to obtain the state space representation for this transfer function. Okay. Now, let us obtain the controllable canonical representation for our transfer function. Okay, so the number of states for a single input, single output system is simply the degree of the denominator polynomial. But in general, if you have more than one input or more than one output, then things may get a little bit, but especially for more than one input, things get a little bit, just a little bit more intricate. Okay, but for our case, we don't have to worry because we have a single input, single output system. But in general, number of states equals number of inputs times degree of denominator, or the common denominator of G of S. Of course, we don't have to worry about the common denominator thing because we have our transfer function is scalar. Remember that. In general, the transfer function does not have to be scalar object. Okay, it's usually in the general case, it's a transfer function matrix. Okay, it's a matrix with entries that are of the form ratios of two polynomials in S. Anyways, so for our case, number of states equals number of individual inputs. In this case, it's 1 because the input is scalar, and the degree of the common denominator of G of S matrix, but G of S is a scalar for our case, and we have just one entry, and the denominator of the degree of that denominator is 5. Okay, so that means we should be able to so that equals 5. So we should be able to obtain a state space representation of dimension 5. Okay, so the rest is really easy for the controllable canonical form. What you do is you choose one of your states as the input being divided by the denominator polynomial, and then from there everything flows easily. So let therefore our last state, okay, be defined as s squared plus, excuse me, s to the 5 2 omega squared s cubed plus omega to the 4 s times the Laplace transform of the input. So this is capital X. So we're in Laplace domain, S domain. Okay, and what this polynomial is no other than the denominator polynomial of our transfer function. Okay, so that's our x5. Why? Well, it's defined in that way. Okay, we choose it that way because it works. And then what we have is the remaining states. x4 is defined as, x3 is defined as, x2 is defined as, and finally x1 is defined as. Okay, so what we do is, now I'm talking in terms of in time domain. x4 is x5 dot. Okay, in time domain, therefore that's how we define it. x4 in Laplace domain is s times x5. x3 is in time domain x5 double dot or x4 dot. So we have s times x4, which equals s squared x5 because x4 was x5 dot. And finally, well, not finally, x2 is x3 dot in time domain, therefore in Laplace domain it's sx3, and which equals s cubed x5, and finally x1 is x2 dot, that is s times x2, which equals s raised to the power of 4 times our fifth state, which we picked first, for x5. Okay, now what we're gonna do is we will concentrate on this equation, which appeared when we defined x5. Now, rewriting this equation yields s to the 5 x5 plus 2 omega square s cube x5 plus omega to the 4s x5 equals the right hand side, which is u. And then what we do is we keep this guy here and throw all the lower order terms to the other side. And we have s to the 5 x5 equals minus 2 omega square s cube x5 minus omega to the 4s x5 plus the input. Okay, and once again we rewrite that equation by remembering that x1 was s to the 4 times x5. Therefore, s to the 5 times x5 is s x1. Okay. Now what we're going to do is we're going to keep all the s times the state variables on this side, and then we're going to express the right hand side in terms of the states without s's. And once we have that, it's very easy to go to time domain, because s times x1 in time domain will give us x1 dot. Okay, and then we were going to write s times x2 in time domain. It's going to give us x2 dot, and so on. And once we have x that equals something times x plus something times u, those somethings will be our A and B matrices. Okay, and once we have A and B matrices, we will then obtain also C and D matrices very easily. Okay, so this s to the 5 x5 is s x1, and that equals 2 omega square s cube x5. Note that now we don't want any s's on the right hand side, so s cube x5 we can express as something, and that something is x2. So this is x2, so we have 2 minus 2 omega square x2. What else? We have sx5. What's sx5? Sx5 is by definition x4. So this we can rewrite as omega to the 4 x4 plus u. Note that there are now no s's on the right hand side. And this was the hardest part. The remaining equations directly follow from the definitions. Okay, sx2, sx3, sx4, and sx5 equals what? Sx2. Okay, sx2 by definition is x1. Sx3 by definition x2. Sx4 by definition x3, and finally here we have x5 dot equals x4. Okay. So this equation transformed to time domain will give us x dot, okay, x being our vector x1, x2 up to x5, x that equals something times x plus something times u, and we're going to obtain A and B matrices very easily from there. Let's also figure out the equation in Laplace domain, which when transformed to time domain gives us the C and D matrices. And for that we have to remember the relation between the output and the input. Well, that relation is described by the transfer function. So let's write our transfer function in a little bit different way. 2s squared plus omega squared. So that's our numerator for the transfer function, times u over the denominator, s squared plus 2 omega squared s cube plus omega to the 4s. Okay, so y equals this thing here is our transfer function times u. Okay, and then we immediately recognize that this object here is our x5. So y equals 2s squared x5 plus omega square x5, okay, because this is no other than x5. And again, we don't want any s's on the right hand side, so we have to get rid of that s square. It's very easy because s square x5 is our x3. So here we have 2x3 plus omega square x5, and this equation y equals linear combination of the states will immediately give us the C and D matrices. Okay, so let's transform our equations into time domain, and we have then our state space representation. Hence, x dot equals a times x plus b times u. No, that x is x1, x2, x5, okay, our state vector. And y equals cx plus du. Okay, this is our A matrix, this is our B matrix, here is C and here is D. Okay, for this equation, let's look at this set of equations that we have derived. As x1 in time domain becomes x1 dot, so therefore this equation will give us the first row, okay, of A and B. x1 dot equals 0 times x1 minus 2 omega squared times x2 plus 0 times x3 minus omega 4 times x4, and finally, not finally, plus 0 times x5 and plus 1 times u. Okay, and then the remaining equations are really easy. x2 dot is x1, okay, x3 dot is x2, x4 dot is x3, and finally x5 dot is x4, and this is our AB pair. How about C and D matrices? If you look at this equation here, okay, y equals 2 times x3, so 0 for x1, 0 for x2, 2 for x3, 0 for x4, and omega square for x5. And as for D matrix, the input doesn't appear here, okay, hence we don't have a D matrix, or we have a D matrix and that's 0. It's a scalar 1 by 1 matrix. Okay, so that completes the first part, part A. Now, by concentrating on that A, we will try to figure out the behavior of the state transition matrix as time goes to infinity. And to be able to do that, we first need to obtain the Jordan representation of that A matrix. Okay, so part B. Characteristic polynomial whose roots are the eigenvalues of A equals determinant of this matrix Si minus A. A is a 5 by 5 matrix, therefore there we expect a polynomial of 5th order. And how about the denominator polynomial? Denominator polynomial of the transfer function. That too is a polynomial of order 5. Now the roots of the denominator polynomial are called the poles of the transfer function, and roots of the characteristic polynomial are called the eigenvalues of the A matrix. Now, the eigenvalues of the A matrix must always be a superset of the poles of the transfer function. So that means if these two polynomials are of the same degree, okay, then therefore this superset equals this set itself, and that's only possible when d of s, the characteristic polynomial, equals denominator polynomial. So in other words, if the degree of the denominator polynomial equals the size of our A matrix, then that denominator polynomial directly is the characteristic polynomial. So since degree of characteristic polynomial equals degree of the transfer function, which equals 5, we have to have characteristic polynomial of A equals the denominator polynomial of the transfer function. Okay, therefore we don't have to compute that determinant as I minus A, because it's already computed here. Okay, therefore d of s equals s plus j omega square s minus j omega square. Okay, when written in that form, all the eigenvalues or all the roots are apparent. Okay, we see them directly. We have an eigenvalue at the origin, a single eigenvalue. We have a repeated pair, we have a repeated eigenvalue at minus j omega, and we have another repeated eigenvalue on on the location j omega. Therefore, all 5 eigenvalues are exactly on the imaginary axis. Okay. Eigenvalues of A equals j omega, another one at j omega, minus j omega, another one at minus j omega, and we have a single eigenvalue on the origin. Okay, now the question is, what's the Jordan form of A? Okay, note that for a given A, Jordan form or Jordan matrix up to a reordering of the blocks is unique. Okay, so therefore we should be able to write down the Jordan form, not a Jordan form for the A matrix. Now, if you know the eigenvalues, writing a Jordan form of a matrix is immediate if all the eigenvalues are distinct. If all the eigenvalues are distinct, okay, then Jordan form is simply a diagonal matrix with entries, with diagonal entries being the eigenvalues. But whenever you have repeated eigenvalues, like we have here, then you have to determine the sizes of the Jordan blocks corresponding to those repeated eigenvalues. Okay. If there is no repetition, like for the eigenvalue at 0, the size of the Jordan block is simply 1 by 1. There's nothing to determine over there. Okay, so J equals, well, first of all, clearly J is of same size as A, 5 by 5 matrix. So that means 5 rows and 5 columns. Okay, this is our Jordan matrix. We can immediately write the diagonal entries, j omega, minus j omega, and 0 for the last eigenvalue at the origin. And then these entries are 0 because according to our convention, the Jordan matrix is always upper triangular. And then what needs to be determined is whether the size, whether the Jordan blocks or block corresponding to, for instance, G omega, the repeated eigenvalue, is or are, okay, is a 2 by 2 single block or two 1 by 1 Jordan blocks, okay? In other words, we have to determine whether this entry A is 0 or 1. If it's 0, it means we have two size 1 by 1 blocks corresponding to the eigenvalue G omega. If it's 1, it means we have a single size 2 by 2 Jordan block corresponding to eigenvalue at G omega. And the same is true for the other repeated eigenvalue, okay, at minus G omega. And then that's it. All the remaining entries must be 0. Okay. Now, depending on the values that A and B can take, we have 4 possibilities. Okay, so let's write them down. There are 4 possibilities for A and B. Okay, both 0, 1 0, 1 1, 1 0, one is 1, the other is 0, and both 1. Okay. Now, if both are 0, then the number of blocks, Jordan blocks, will be 5. So L, which was the notation that we used to indicate the number of blocks, L equals 5. L also is the number of linearly independent eigenvectors of the A matrix or the J matrix. And here we have L equals 4, and for this case, number of linearly independent eigenvectors must be 3. Okay. Okay, now we have to determine, if we can, what the values that A and B should take. Now here is the claim for the value of A. The claim is that A must equal 1. Okay, in other words, the Jordan block corresponding to eigenvalue at G omega must be size 2 by 2. So let's try to demonstrate this statement. And what we're going to do is, we're going to do that by contradiction, a very powerful, when applicable, proof method. Suppose not. Okay, so we're going to consider that this statement is false, and then we're going to try to figure out the consequences. And if you reach a contradiction, so that means the statement cannot be false. So that's proving it in backwards way. Okay, so if this statement is false, then A must be 0. Okay, because there's no other choice. We're talking about the Jordan representation. Then okay, we can proceed as follows. Rank of J minus J omega times identity matrix. Okay, so that equals 0 0 0 0 0. That equals the rank of this matrix. 0 0 0 0 0 0 0 minus J 2 omega B 0 minus J 2 omega 0, and here finally we have minus J omega. Okay. Now this is a 5 by 5 matrix, and two of its rows are 0, okay, or 2 of its columns are 0. So its rank cannot be larger than 3, okay. And then by looking at this sub matrix here, that block here, we see that the rank of this block is 3, and that will be inherited by, that means the rank of the mother matrix cannot be smaller than 3, but we know that it cannot be larger than 2, because it has 2 0 columns. So that means the rank of this matrix J minus J omega I equals 3. Now, this seems like an arbitrary step which seems to have nothing to do with what we're trying to prove, but just be patient until it becomes useful. Now what we're going to do is we're going to compute the rank of A minus J omega I. Okay. So that equals rank of this matrix minus J omega minus omega square 0 minus omega square omega to the 4, and this is, excuse me, 2 omega square. Okay, and here we have 1 minus J omega 0 0 0 0 1 minus J omega 0 0 0 0 1 minus J omega 0, and finally 0 0 0 1 minus J omega. Okay, and then let's consider this submatrix because of its upper triangular form and because it has ones or non-zero entries on its diagonal form. The rank of this 4 by 4 matrix is 4, its full rank, and therefore the rank of the mother matrix cannot be smaller than 4. So what we have obtained is the rank of A minus J omega I must be at least 4. Okay, and then let's combine these two things, and that will give us a contradiction. Now, so what we have is 3 equals rank of J minus J omega I. Okay, so that's what we obtained here. Then that equals rank of, let's rewrite J in terms of A. Note that there's a change of coordinates matrix, change of coordinate matrix, which is necessarily non-singular, that takes J to A, and its inverse will take A to J. In other words, we have to have some P such that PA, P inverse must give us J minus J omega I. And that equals rank of, we can take P's out, A minus J omega I P inverse. Okay. Now this I you can write as P times I times P inverse, and then you can take those P and P inverses outside, and this therefore clearly equals that. And that equals rank of, now P is non-singular because it has an inverse. So this is non-singular, this is non-singular, and non-singular matrices cannot decrease the rank. So what we can, or they don't affect rank, so what we do is we can take P and P inverse out and still have the same rank. Okay, so rank of A minus J omega I. And we know that rank of A minus J omega I cannot be smaller than 4. Therefore this is greater than or equal to 4. Okay, now what we have obtained therefore is 3 is greater than or equal to 4, which obviously is wrong. So that's a contradiction to our initial assumption. Hence our initial assumption cannot be true. This was our initial assumption, and hence A must be 1. So that's the end of the proof. Okay, so likewise, let me squeeze it here. One can show that B must be 1 also. And since A and B are determined, now we have our exact Jordan matrix representing our A matrix. Okay, hence J, the Jordan matrix, equals or has 3 blocks, J1, J2, and J3, okay, where J1 equals this guy here, J omega 1, 0, J omega. J2 equals this guy here, minus J omega 1, 0, minus J omega. And J3 is here, a 1 by 1 block. So we have 2 2 by 2 blocks and 1 1 by 1 block. The total of 3 blocks, meaning that the A matrix has 3 linearly independent eigenvectors. Okay, now since we have the exact Jordan matrix in our hands, we can say for certain the behavior of the A matrix or state transition matrix as time goes to infinity. Okay, so let's do that and finish our example. E to the A t goes to what? Okay. From our previous lectures, we know that if the A matrix has an eigenvalue with strictly positive real part, then state transition matrix must blow up. Now, in our case, we don't have any eigenvalues on the open right half plane. Okay, therefore we cannot use that condition. Now, how about the case when all the eigenvalues are on the closed left half plane? So if that's the case, e to the at could either be bounded, okay, or in the extreme case it may converge to 0, or unbounded. And to determine whether it's unbounded or not, what we have to do is you have to check the sizes of the Jordan blocks corresponding to the eigenvalues on the imaginary axis. Okay? Well, in this case, all our eigenvalues are on the imaginary axis, and we have, for instance, for J omega, a size 2 by 2 Jordan block. Okay? So whenever you have a size 2 by 2 or larger Jordan block for an eigenvalue on the imaginary axis, then your e to the at is unbounded. So as time goes to infinity, its norm grows and grows. Okay, note that suppose that our first eigenvalue is J omega. Suppose that for the eigenvalue J omega, which is on the imaginary axis, therefore its real part is 0. The size of the block is 2 by 2. Therefore, e to the at has to be unbounded. We don't have to check anything else, because once we have unboundedness for one of the eigenvalues, the rest is immaterial. Okay. Now, in particular, we have unboundedness because, well, J1 will yield e to the J1t, so its state transition matrix for this 2 by 2 matrix is e to the J omega 0, e to the J omega, and e to the, t, and e to the J omega t is just sines and cosines oscillating at frequency omega radians per second. But, so they're not harmful, they're always bounded, but this term here has a t multiplying it. Okay? So this is zero, no harm. These are bounded, but this guy, because of this t, will produce something like that. Oscillations whose magnitudes are growing in time. Because of that, e to the jt will grow unbounded because e to the jt has this form, e to the j2t, e to the j3t. Okay? This is the state transition matrix corresponding to our Jordan matrix. So clearly, since this term is growing, is unbounded, e to the jt is unbounded, and finally, e to the at is unbounded because e to the at can be written as p inverse e to the jt times p. Now, since those p matrices are constant, they cannot suppress the unboundedness of e to the jt. In other words, unboundedness of e to the jt will be inherited by e to the at. So we can write, therefore, that our state transition matrix is unbounded.